Well, this video is about acids and their strength. How do we know when one acid is stronger than the other? And I'm going to be talking about these three rules here. So let's just start from the top. The more polar an HX bond, so HX is really, in this case, is going to represent any kind of acid. So an acid will lose a hydrogen, so anything, any kind of anion attached to a hydrogen is going to be representing an acid here. So the more polar this bond is, as in the more positive this side is and the more negative this side is, or we usually use these arrows, the more polar the bond, the stronger the acid. So taking a look at an example of that, if we look down here, I've got OH groups, so it kind of sits like this. Like this is where the bond's going to break and let this hydrogen leave. Acids lose their hydrogens. So the more electronegative this part is, the more partial negative is on this side versus the partial positive on this side. The more negative it is on this side, which is controlled by electronegativity, in this case Cl is the most electronegative element of my 4. The more electronegative this is, the stronger the acid. You can see the Ka here is 10 to the negative 8, which is stronger than all the rest, the bottom one being 10 to the negative 14. Water, OH, although the O is very electronegative, the H that it's attached to is not very electronegative over here, so that doesn't really pull the electrons as well as the chlorine does. So the more polar this bond can be, by having more electronegative things on this side, the stronger the acid is, because the H can leave easier. Rule number 1. But that kind of poses a problem, though. If we take a look at our halogen group right here, this is the last group. Here I've got HF. We know F to be the most electronegative. He has a electronegativity of 4, and here's hydrogen attached to him. Then you have chlorine. I think he's like a 3.5 or something. Don't quote me on that. He's a 3 point something. And then bromine as we go. But as we go down, it becomes less electronegative. So it would say to us, if fluorine is the most electronegative, then we would think that this HF is the most strongest acid of the group. But that's not true. We can see the opposite is true. And that's because of size. That brings me to rule number 2. A weaker HX bond will lead to a stronger acid. So let's take a look at bromine. Bromine is the fattest of this group that we're looking at. So bromine is a very big ion. And it's attached to a little H. Up here we've got fluorine. Fluorine is a small, so here he is, and he's attached to an H. If we apply Coulomb's law to this bond right here, according to Coulomb's law, the distance is so small according to this distance, which is so great. We know according to Coulomb's law, the greater the distance, the weaker the attraction, thus the weaker this bond is, and it can more easily leave. That brings us to rule number 2 again to repeat. The weaker the HX bond, this is a weaker bond, the stronger the acid. So although this group has to do with electronegativity, in this case the trend follows where you get a stronger acid as you go down because of Coulomb's law, which creates a weaker bond, and the hydrogen can leave easier. Moving on to rule number 3, more stable conjugate base. So I want to kind of show you, that's a boot. I want to kind of show you something different here. More stable conjugate base. So here are 4 different acids. And we're going to increase our strength of acids as we go to the right. I want to recap what a conjugate base is. So we have an acid. When the acid loses the hydrogen, that's a conjugate base. So right here is my acid. If I take this all the way out, the thing that I have left over is a conjugate base. So let's take off all these hydrogens to create conjugate bases. If I do that, I'm going to scroll down here. This is what the structures actually look like. So you can see that this one on this far left, which is the weakest one, will be at the top, and this one will be at the bottom of my chart down here. So here is my strong acid down at the bottom. Here's my weak acid at the top. Can you see how these strong acids at the bottom have severe resonance structures going on? All of these resonance structures creates a very stable conjugate base. Which brings me to the more stable the conjugate base, the stronger the acid. Conjugate bases are going to be really stable when you happen to increase the number of atoms that electrons can kind of move around in. We can see there's 4 oxygens here, 3, 2, and 1. With acids, it's kind of common to have a bunch of oxygens in a ring. The more oxygens you have in a ring, the more kind of resonance structures you could have, the more stable conjugate base, the stronger the acid. There we are. That kind of brings me to this structure. All of these have something in common. They all have this group right here. It's called a carboxylic group. This one here is acetic acid, or ethanoic acid. It's vinegar, this top one. But you can see all of them have the same structure, and it actually creates a big stability kind of area for it. When we do its conjugate base, that means this hydrogen is leaving on all of them. You can kind of create this resonance structure. This double bond moves between the two, back and forth, and that resonance structure creates a very stable conjugate base. That's why these carboxylic acids, you want to look for these kind of groups right here. These kind of groups make a pretty great acid. Not a strong acid necessarily, but a good acid that gives it a lot of strength. Alright, I hope that helped.